Alrighty, next up we have the ideal gas law. Again, all of the gas laws, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, they're all mathematical equations that show relationships between properties of a gas. I haven't given you any of the other gas laws. We've solved those problems differently. But this time I'm going to give you the equation. So here it is. The ideal gas law reads PV equals nRT. So P is the pressure of the gas. Now in your notes it says in atmospheres, but it doesn't have to be. So this will have implications in just a bit, as we'll see. So it could be in atmospheres, it can be in torr, millimeters of mercury, or kilopascals. V is the volume, has to be in liters. So if it's not given to you in liters, convert it to liters. N, as we saw before with Avogadro's law, is the amount of the gas in moles, not grams, so be careful. And then R is called the ideal gas constant. It's just a proportionality constant. So it helps to turn the proportion into an equality. So we get PV equals nRT, not PV is proportional to RT, or to NT rather. The value for R depends on the pressure, the units of pressure for P. So if P is in atmospheres, then the value of R is 0.0821. So I mentioned before, atmospheres are the most common unit of pressure used in chemistry. In fact, that makes then this R the most common value for R, but there are others. So if the pressure, let's say, is in torr or millimeters of mercury, then R has a value of 62.4. Take a look at the units. So we have liter atmosphere per mole Kelvin is how we read that. Or in this case, liter torr or liter millimeters of mercury. Remember, millimeters of mercury and torr are the same thing. Liter torr per mole Kelvin. And if the pressure is given in kilopascals, the value for R is 8.31 liter, whoops, that should say kilopascals, not atmospheres. Liters times kilopascals over mole Kelvin. So choice is yours. You can either memorize all three values of R or memorize one. If you memorize one, I would go with the 0.0821. And all that means is if your pressure is not in atmospheres, you need to convert it to atmospheres. So how do we convert, say, millimeters of mercury to atmospheres? Well, you can use the values for standard pressure and use those as a conversion factor. So it works for all of them. So choice is yours. And lastly, temperature, of course, is T. That temperature has to be in Kelvin. So the ideal gas law can be helpful for when you have a gas not at STP. So we did some calculations involving gases at STP where we can convert, say, between moles and liters using the standard molar volume of a gas, 22.4. But we can convert between moles and liters of a gas when not at STP. So we just have to use this formula, the ideal gas law. All right, let's take a look at an example. First one, how many grams, so we're looking for mass of a gas, how many grams would 10.0 liters of carbon dioxide gas not at STP weigh? Now again, if this is done at STP, we take 10 liters, convert that to moles using 22.4, and then convert that to grams using molar mass. But we're not at STP, so we cannot use 22.4, so we're going to use the ideal gas law. So let's take a look again at that equation. So we have a gas at 23 degrees Celsius, 1.10 atmospheres. Let's see what we know, and more importantly, what we don't know. So it looks like we know the pressure of the gas, we know the volume, and we know the temperature. You always know R, that's a constant, so we don't have to worry about that. So what don't we know? Well, we don't know moles. So let's do that. Let's solve for moles. So I'm going to divide the equation by both sides by RT. So we get N equals PV over RT. And then once I determine the number of moles of the gas, I can use molar mass to find grams. So let's go ahead and do that. I'll guide you through this first one, then I'll have you do some on your own. All right, pressure is 1.10 atmospheres. So plug that in here up top. Volume 10.0 liters. Since our pressure is given to us in atmospheres, or since we plugged it in atmospheres, we need to use the R that has atmospheres in it so that it cancels. So that's 0.0821. I know your notes gave you more than just 3 sig figs, but this one will be fine. 0.0821 liter atmosphere per mole Kelvin. And then the temperature, 23 degrees Celsius converted to Kelvin, is 296. All right, so let's take a look at the units. Let's not worry about the number, numerical answer just yet. So atmospheres cancels, liters cancels, Kelvin cancels, so we're going to be left with moles. Go ahead and pause the video and punch that up. Now, something that's very important to understand, not so much in this one, but it will later, is what is it? So you get 0.453 moles. Moles of what? Well, what is the 1.10 atmospheres of pressure of? That's the pressure of the carbon dioxide. And what is the 10 liters of? That's 10 liters of carbon dioxide. 23 degrees Celsius, that's the temperature of the carbon dioxide. So when we plug all that stuff in, what we get is moles of carbon dioxide. All right, I'll let you finish this problem. Now that we have moles of carbon dioxide, we can use the molar mass to find grams of carbon dioxide. Go ahead and pause the video and get that answer. Even though I didn't show it, I expect you to show the work. So we have 44.0 grams of carbon dioxide over 1 mole carbon dioxide, and multiply that by 0.453 moles of CO2, and we get 19.9 grams of carbon dioxide. All right, go ahead and try this one on your own. This time we're looking for volume given the mass of oxygen gas. Be careful again with those diatomics, especially when we're determining molar mass. So go ahead and pause the video and solve this one here. Pause now. All right, here's my setup. You get 15.4 liters as your answer. If you broke this up into steps, multiple steps, that's fine. So you could have taken the grams of oxygen, converted that to moles first. And so we get 0.625 moles of oxygen. Likewise, you could have taken the pressure in millimeters of mercury and converted it to atmospheres and then plug that in. So that would give you 1.01 atmospheres. If we round that, it's 1.00789. So 1.01 atmospheres, plug those values in and then solve for V. So notice I took our equation ideal gas law, isolated V. I did so by dividing both sides by P, plugged everything in, and we get our answer. All right, one more. This time we're finding pressure. So start with the ideal gas law, rearrange it, solving for P. It asks specifically for the pressure in kilopascals, so you can do this one of a couple of different ways. I'll let you decide, and I'll show you which way I chose, and then we'll compare answers. So go ahead and pause the video now, please. All right, so once again, I just plugged in the mass along with molar mass to find moles, but if you did that separately and took that 13 grams of hydrogen converted to moles, you get 6.44 moles. I decided to use the R that has kilopascals in it. If you use 0.0821, that's fine. You're just going to get your answer in atmospheres. That would be 57.7 atmospheres, and then you can take that and convert it to kilopascals using standard pressure in kilopascals and atmospheres. Ultimately, we should get this. We want 3 sig figs, I believe, in the answer. So 5,840 kilopascals, which is pretty darn high. All right, let's try something else. We have some gas stoichiometry. We did some stoichiometry problems before, but what's different about those compared to this problem here and the next one we'll do is that the problems we've done in the past, the substances were at STP, and so we were able to just use mole conversions to do that calculation. Well, what if the gases are not at STP? We can't use just mole conversions. We can't use 22.4. And so what we're going to do is we're going to use both mole conversions and the ideal gas law. Sometimes you'll use the ideal gas law first and then mole conversions second. Sometimes you'll use mole conversions first and then ideal gas law second. So it just depends on what you're given and what you're doing. So be careful. All right, this one says 17.0 liters of carbon dioxide are produced from the combustion of some methane. So this is a stoichiometry problem. We're given the amount of one substance, carbon dioxide, and asked to find the amount of a different substance. 17 liters carbon dioxide at a pressure of 700 millimeters of mercury and a temperature of 100 degrees Celsius. How many grams of methane burned? Okay, so we're given the volume of carbon dioxide. We're going to use that to find what first. So what are we doing first? Ideal gas law or mole conversions? So, well, given that this gas is not at STP, I'm guessing we're not going to do mole conversions first. We'll do the ideal gas law. All right, just like in any other stoichiometry problem, first thing we need to do is write the balance equation for the reaction. So let's go ahead and do that. It's important to include states of matter in your equation because you can't plug in the amount of a non-gas to the ideal gas law, so you want to be careful of that. All right, so we're given the amount of carbon dioxide, trying to find the amount of methane. So let's do this. I'm going to have you do this first part. So go ahead and take the volume of the carbon dioxide, the pressure and the temperature of carbon dioxide. Use those to find moles of carbon dioxide using the ideal gas law. Go ahead and pause the video and we'll compare what you get. Don't answer the question, just find moles carbon dioxide. Pause now. Okay, so given the volume, pressure, and temperature of carbon dioxide, I plug that into the ideal gas law to find moles of carbon dioxide, which is 0.511. And then we want to convert that to moles of methane and then grams of methane. So let's finish this off. We have 1 mole of carbon dioxide for every 1 mole of methane, according to our balanced equation. I did that backwards. That's why it's important to label everything. So let's go back. That's 1 mole of methane per 1 mole of carbon dioxide. All right, now we're good. Okay, and then convert the moles of methane to grams of methane. Molar mass, I believe, is about 16.1, 16.0, 16.1. I'm good with either one. Go ahead and pause and see what you get. All right, we should end up with 8.18 grams of methane that reacted, or grams of methane that burned during this reaction. So again, we got ideal gas law and mole conversions. This case, we use the ideal gas law first. All right, let's go ahead and try this one on your own. We have 46.0 milliliters of hydrogen gas produced from the decomposition of water. This reaction was carried out at 25 degrees Celsius and 800 torr pressure. I believe it's written differently in your notes. I want you to answer this question, not the one that's in the notes. How many grams of water decomposed? So it doesn't really matter, but let's go with liquid water in this reaction. Go ahead and pause the video and set this up. All right, hopefully my math is right here. So first thing, I want to take that volume and convert it to liters, since again, R has units of liter times some unit of pressure per mole Kelvin. So take the volume divided by 1,000. I think I did that right, looks good. Multiply by pressure divided by R and T, and we get 0.00198 moles of hydrogen gas that is produced in the reaction. And then we apply our mole conversions to ultimately find grams of water. Not a lot of water, 0.0356 grams of water. That's a really small amount as needed to produce 46 milliliters of hydrogen gas at that temperature and pressure. All right, let's try one more just to warn, well, actually one more of these types of problems. Just to warn you, this is probably the toughest of the 3 so far. A single replacement reaction occurs when lithium metal is placed in a solution of hydrochloric acid. 18.0 grams of lithium react during this process. How many milliliters of hydrogen gas will be produced at a pressure of 105 kilopascals and a temperature of 22 degrees Celsius? All right, start off with a balanced equation for the reaction and set up the calculation. Go ahead and pause now. All right, this time I'm not going to set it up for you right now because I want to make sure that you know what you're doing. And so I want to check before you get to know what the correct answer is. So we'll come back to this later. During class, we'll discuss the answer to this. And if there's any issues about the setup, we can go over it then. All right, let's change it up. A little different problem. 4.05 grams of an unknown gas occupies 1.50 liters at a pressure of 1.50 atmospheres and a temperature of 25 degrees Celsius. Calculate the molecular / molar mass of the unknown. So we've done this before where we've determined the molar mass of an unknown substance. So recall, to determine the molar mass of an unknown substance, we need the mass of the substance, which I'm pretty sure is given to us. And we need the amount of the substance in moles, and we'll divide that. Well, we're not given the amount of the substance in moles. What do we know about the gas? Well, we know its volume, we know its pressure, and we know its temperature. Think we can use those to find moles of the gas? I think so. So go ahead and set this one up. If you want to do it on 2 separate steps where you find moles first and then plug that in along with the mass, that's fine. Go ahead and pause the video now. All right, here's the setup. So we find moles using ideal gas law. So you get 0.0920 moles of the unknown gas. Take the mass of the unknown, which is given to us in the problem, divided by moles that you calculated, and we get 44.0 grams per mole. Technically, since the question asked for the molecular mass, really this is the best answer. We want to give the units in AMUs, so we get 44.0 AMUs. All right, one more. 3.0 liters, 3.00 liters of ethane gas, C2H6, at 20 degrees Celsius and 103 kilopascals are mixed with 5.00 liters of oxygen gas at 18 degrees Celsius and 110 kilopascals and allowed to react. So this is a combustion reaction. What volume of water vapor at 150 kilopascals and 100 degrees Celsius will be produced? So notice something. Let's start off with our balanced equation for the reaction. I'll let you balance that. Go ahead and do that now. Let's include some states of matter. Ethane is a gas, oxygen is a gas, carbon dioxide is a gas, and water vapor is a gas. So what are we going to start with? Well, if you notice, this one's a little bit different. We're given the quantities of both. By quantities, I mean the volume and the temperature and the pressure of both the ethane and the oxygen. So this is, as you guessed, a limiting reactants problem. So we're going to want to find moles of ethane and moles of oxygen, and then compare that available ratio to the needed ratio being 7:2 or 3.5 to 1. And then once we identify the limiting reactants, then we can use that to answer the question. So go ahead and pause the video and set this up, find the limiting reactants, and then once you know that, use that to ultimately determine the volume in liters of water vapor that forms at that pressure and temperature. Go ahead and pause now. So using the ideal gas law for both the ethane and oxygen, I found 0.127 moles of ethane, 0.227 moles of oxygen. When you divide those, you get a less than 3.5 to 1 ratio available. That means that oxygen is the limiting reactant. You need more oxygen than you have available. And then I'll take that 0.227 moles of oxygen, use that to find moles of water. Plug that into the ideal gas law along with the pressure and temperature of the water vapor. and we get 4.03 liters of water vapor that is produced. All right, kind of a lot of stuff there. We got ideal gas law, gas stoichiometry, limiting reactants problems, molar mass of unknown gas, quite a bit of stuff to keep track of. Thanks for watching, and we'll do some more next time.